So today we are going to cover a lot of different topics. We have 6 talks plus 2 contributed talks. So we should start going. Before that,
quick reminder.
Quick reminder of to be a bit of the code of conduct of the meeting. So I don't think I will repeat all these. If you run into issues, please reach out to point of contact. Also, to be mindful of others in the room and online. When you speak, make sure that people in the room and who are online can see and hear what you're presenting, and make sure that the questions are here from both sides. And so today's agenda will be, we'll first have Melissa, Graham, and Bryce to talk about the Rubin data management PhotoZ roadmap. Julia will give an update on the software development, Linea, and the advanced data products to support Rubin's PhotoZ production. I will talk about Rails update and give a live demo, and we'll be followed by 2 talks about specific PhotoZ methods. The first would be the DeepDISC PhotoZ, which is a deep learning methods on image-based PhotoZ estimation, and Photometric Redshift with RAIL-LePhare, which is template-based method. We'll have 2 contributed talks from Noah on direct Redshift calibration, and from Simona on image-based machine learning PhotoZ methods.
And for remote participants, please put your questions on Slack, and we'll use that to manage Q&A.
Hi everybody, I'm presenting update on the Rubin PhotoZ plans on the project side. These were prepared by Malz and Graham, who's kind of running the PhotoZ commissioning team. I'm Bryce Kalmbach, also from the University of Washington, and along with Sam Schmidt, who's remote, from the co-conveners for the DESC PhotoZ working group. All right, so as part of the annual data releases that Rubin provides, there will be photo Z estimates as part of the object table. The object table is the data that comes from the deeply co-edited images. And so there's room in there for photo Z estimates. And so DM is going to provide 1 or more existing community vetted algorithms, results from those. But there's still work to be done on exactly what is going to go into those. We'll talk a little bit more about kind of the roadmap and timeline. So who is going to be generating these photo Zs for the object tables? Rubin data management. There's also a Rubin photo Z commissioning team. I'm going to talk a little more about kind of various parts of this in later slides. There's also international in-kind contribution teams, like the contribution from Brazil through Linea, which I think Julia is going to talk about later. There are efforts from science collaboration members like DESC and others, link frameworks. There's the PhotoZ validation cooperative, which we'll say more about at the end, and just the broader Rubin science community, which can be kind of engaged through the community .lsst.org. So the timeline here, we're kind of in the middle of this timeline, which started about 3 years ago with a call for letters of recommendation. In February 22, the summary of those letters of recommendation were released, and kind of a shortlisted set of photo Z estimators that DM will look at implementing or using was announced. The PZ commissioning team was formed. The PZ commissioning team is we meet roughly once a month. And there's a group of us that meet online and kind of discuss progress and are getting ready for commissioning data to start working on that. Data preview 1, data preview 2, these will all be really important times for the commissioning team and the validation cooperative. And then by the late 2026, DM will release its final decision on what will go into that object table in terms of PhotoZ information. And 27, they release one more. So this letters of recommendation that kind of kicked this whole process off. There were 20 submissions. There were 13 submissions that pushed for a particular estimator from either users or developers of those estimators. 6 described kind of science use cases from various members of the Rubin science community. And then there was one from DESC, which Alex, Malz, and Sam Schmidt kind of put together describing DESC's PhotoZ work. At the end of the process, 5 estimators that were well established with performance kind of that's well used in the community and that was trusted. They were announced as the short list. So this is GPZ, again, RAIL-LePhare, and VPZ. It doesn't mean that these are going to be the final ones, or that any of the other ones that submitted will not be considered. It just means these are the ones that are going to be prioritized at the moment because we know the most about them. And then there's more information at that link. So the PhotoZ commissioning team, like I said, we started meeting roughly once a month. We're working on kind of developing the infrastructure to validate the PhotoZs on the commissioning data. We've done some work learning about what goes into the object tables and everything from DP0, and then working on methods and tools we're going to use to do the validation once the commission data starts rolling in. So there's other kind of tasks for this team that you can see here. And we'll really get ramped up once data preview 1 arrives. And so members of this team come from DM, from the broader science collaborations, in-kind efforts, and so there's also the PhotoZ in-kind coordination group. This is just to make sure that the various in-kind efforts are kind of not duplicating work. They're working together on useful additions to the PhotoZ roadmap, and kind of taking in and working with the broader science community to make sure that the in-kind efforts are actually going to be what the community needs. And so kind of discussions on that can be accessed here to the link on community.lsst.org. So the PhotoZ validation cooperative will be actually in charge of doing the science validation once we have data to work on. So starting with DP1 early next year from ComCam, and really getting going with DP2 with the LSST science camera imaging data starts rolling in. So when that starts, we will start kind of developing PhotoZs, testing them out, running the estimators, and using input from the science community to make sure that the PhotoZs are ready for science. And if you are interested in kind of seeing what that might be like, you can use DP0 to kind of get an idea of what it's like to run PhotoZ estimators on LSST and Rubin DM outputs, and just keep an eye on the community.lsst.org subject, PhotoZ category, PC category. So yeah, so the DM is going to need a lot of help from the broader science community because their efforts are limited, and they're really going to be seeking out the experts in PhotoZ or the users in PhotoZ to know exactly what to put in, because there's limited space in the final object tables, and there's a lot of broad interest in PhotoZ, and what the DM team wants to make sure that what they put in there will be the best thing for the broader science community. So keep in touch on community, and then we're going to hear about all the other work in the broader science community based on PhotoZ that's happening right now. And so that's it's good that you're here. You're interested. And if you have further questions, you can contact Melissa and ask me later. I think that's it.
Here's some time for questions.
Any online?
Slack?
Okay, great.
Thanks, Bryce. I think next up we have Julia. I'll just drive the slide. for Julia.
Hello, can I share the screen? Is it possible?
Yeah, I can switch the slides for you, or you can try.
I'll try. Okay.
I see your hand up. Can you put it on Slack?
Okay.
Julia, please. Thank you.
Hi, everyone. Thanks for the opportunity to share our work in progress with you. The Brazilian in-kind contribution program includes a light version of an independent data access center and a couple of software development efforts, including a section dedicated to the production of PhotoZs and also ancillary data products related to PhotoZs. So we are very happy to have our in-kind contribution agreements signed recently. I have been reporting the progress of our work in previous meetings like this one, so will introduce briefly the topics for new people in the audience and try to focus on the recent updates. So one main aspect of our contribution is the PZ server or PhotoZ server. This is a service hosted at the Brazilian IDEC to create, store, and allow users to share PhotoZ products, the related data products. It can be accessed two ways, through the PZ server website or through the Python library, PZ server library. The data products can be uploaded by any user. There is a list of initial product types allowed, but this list might be expanded depending on user requests and also depending on approval by the recipient group. The recipient for our contribution is data management team, and Melissa Graham is our main point of contact. Together with data, users can upload auxiliary description files. For instance, they can upload the Jupyter notebook that was used to create that particular data set and in its HTML version, including output figures. And once the data products are uploaded, they can be listed in a page. There's a list where each data products is a clickable link that goes to its details page. The details page shows the description file when it is provided by the user, and also the first 10 rows of the catalog as a preview when the data is tabular kind of data. And another way to interact with the PZ server is via the Python library. So users can use the PZ server class to upload and download data and to display metadata and to search for data products. The library can be used from anywhere, including the notebook aspect of the Rubin Science platform. And the class will connect remotely with the PZ server backend running in Brazil through the internet. The PZ server also has a cross-matching service to create a combined spectroscopic redshifts catalog that put together data from different surveys, and also to create training sets from the matching of these individual catalogs or the combined catalogs matched with the LSST object catalogs that will be available on the IDEC file system. So these pipelines are under development. They use HipScat and LSDB from Link as backend, and they will be possible to be triggered both through the Python library and the PZ server website. This is the prototype of the training set maker screen on PZ server website. It's very preliminary. And an orchestration layer will manage the process that will be started by different users and send them to be executed in the cluster. Well, about the authorization and authentication of the users, nowadays in the development environment, they are being done with GitHub credentials, but soon all the Brazilian IDEX services will be accessed via CI logon in sync with the Rubin Science Platform authorization system. So any Rubin Science Platform user will be able to access the PZ server using the same credentials without needing to have a separate registration. And if you'd like to access the development environment right now and give us your early feedback, there is an invitation link here in the slides, and I will also post it in the Slack channel for this session after the presentation. And now moving on to the next topic, which is the pipeline PhotoZ compute or PZ compute. It is a software layer to connect RAIL estimate module to the Brazilian IDEC high performance computing infrastructure, which includes HPE Apollo 2000 cluster with 1072 physical cores and 570 terabyte storage on a Lustre system. The role of this pipeline is to control all the cluster configuration and data partitioning variables in order to extract the maximum performance of the system. So the optimal configuration might vary, might be different depending on the data and also depending on which PhotoZ algorithm is being used at the moment. The core part of the pipeline is already running in production mode, but all the data transfer workflow is still under construction. We have been doing performance tests since last year to mimic the full LSST final object catalog with 40 billion rows and perform stress tests on the system. We just make multiple copies of the DP 0.2 catalog and run on it. There are 3 algorithms already configured and ready to produce results. They are BPZ, FlexiBoost, and TPZ. And the next one will be GPZ. There is an open pull request already for it. And after that, we are going to focus on implementing support to the template-based algorithms from the shortlisted codes in the PZ roadmap document. Last year, Eloisa presented a poster with the first round of results of performance tests. And since then, we implemented support to TPZ, and also we have been doing fine-tuning on the system. And according to our latest results, we can produce PhotoZ PDF tables for the entire catalog for all these 3 algorithms in less than a day. However, particularly for BPZ, this estimate might be too optimistic if you consider that the total duration of the process will scale with the number of SED templates used. And now in here, we use just a default set of 8 templates. Recently, we started looking more carefully at the input data and the training procedure using RAIL-Inform module, and so that the results of these tests could also pass through a scientific validation and be useful to be shared with DP0 delegates through the Rubin Science Platform. So this is work in progress. We have not shared any results with our recipients yet. But anyway, I invite you to check out Andrea's poster during the coffee break today. Andrea and her supervisor, Bruno Moraes, have been working on the end-to-end tests to validate the whole process, to help us to validate the whole process, which has been tremendously helpful for us to identifying both scientific and technical issues that should be addressed and improved. And for instance, identifying data flow or data process bottlenecks, also identifying some procedures that need consistency checks to avoid human mistakes where it is not possible to have 100% of the steps automatized. So I finish here with a summary of the previous slides. Besides this software and infrastructure, we also contribute with FTE, hours of work to participate in the commissioning activities. This is my email. Please contact me if you have any questions or suggestions. And I'm also happy to answer any questions now or later on Slack. Thank you.
Any question for Julia?
There's one on Slack from
Go ahead.
From Simona. Is the Linnea tool the only archive where the PhotoZ catalog will be shared?
Sorry, I cannot hear Alex very well. Hey, Alex, I will try to read from Slack directly. No, actually, we are going to produce an alternative PhotoZ. It's not the official one that was mentioned before. So we are going to be one of the places where data will be shared. However, the main PhotoZ catalogs will be delivered to the US data facility and distributed through the Rubin Science platform, as well as the official one.
So I have a question about the data format that you're planning to share. So are you putting the PhotoZ output into catalogs that are accessible by Butler, or is it in a different way of queuing and getting the catalog? Like how is user getting the PhotoZ output?
Yeah, no, we are not having an instance of the Rubin Science platform here in the Brazilian IDEC. As a light IDEC, we are just going to provide catalogs and not images. So we are going to use our own platforms to provide access to the data. So we have no Butler installed here. So when we upload the results back to Rubin Science platform, and that will be required an extra step to make those those outputs in the right format to be readable through using Butler.
Okay, understood. Thank you.
Stick to time. I think we'll get to the next speaker. I'll put another question on Slack. Anyone with more questions can also put them on Slack. Thank you.
Thank you.
Julia. Could you stop sharing? Please? Thank you.
Sure. Yeah. Thank you.
So next up, I will be giving an update on Rails development on behalf of Rails developer team. So before talking about Rail, I want to talk about the challenge we face in doing research in PhotoZ world and also doing production in PhotoZ world is that if you go into any review paper of PhotoZ methods developed in the past few decades, you'll find that there are dozens of methods that are developed. They're categorized into physics-driven or sometimes called template-fitting code or into data-driven. It's normally done with some kind of machine learning or statistical modeling. But the gist of this is that the expected input and output coding language they're using, handling of corner cases are all different for dozens of methods. So this makes it really challenging to do science on PhotoZ, to compare performance in terms of science or in terms of computing, and to make production in terms of saving configuration of multiple different runs, very challenging. So RAIL is designed in the first place within DESC by Alex and Sam, and later developed by lots of RAIL developers to solve these issues. The RAIL is an open source software libraries to provide a platform for PhotoZ production and study. It is originated in DESC and currently based in DESC, but it's also envisioned to serve other broader LSST extra-connected community. So developer of RAIL includes DESC pipeline scientists, Link framework software engineers, and project scientists, and DESC in-kind contributors, Rubin white contributors, and others in the open source software community. So for the interest of time, I'm not going to great detail of technicality of RAIL, but the basic idea of RAIL is that RAIL functionalities are built in stages, and you can think of it as carriages of trains. We have different kinds of carriages, but they can all get connected and run on the same rail. So RAIL is sort of providing that infrastructure for these different kinds of functionalities. The workflow is based on SETC, a different workflow manager of DESC. The PhotoZ output is written in the format of QP, a generic library for 1D PDFs, and RAIL methods are building sub-packages that are streamlined by Python project templates and one Python framework, which makes a new package really quick. So I'm going to talk through a few different kinds of RAIL stages. So first and foremost, we have the two core kinds of stages, one called informer and the other called the estimator. And I want to mention that RAIL stages really expect a fixed set of input and a fixed set of output. So for the informer stage, it will expect the training set of the PhotoZ and produce a model. That's all it does. For the estimator stages, it will expect the model trained by the informer and the photometry, and it will produce PhotoZ and write it into a format that's recognizable by other stages. For cosmology, it is important to categorize galaxies into different tomographic binings. So we create this classifier stage to assign tomographic binning, and also the summarizers to produce redshift distribution. So here's a long list of the methods RAIL are trying to incorporate into the library. The methods in black is the methods that are already released, and those in gray are work in progress. So you can see we have two kinds of template fitting code, BPZ and LePhare, which we'll hear in the later talks. We have a bunch of machine learning methods ranging from simpler models like KNN to complicated model like FlexiBoost. And I won't go into detail of each of them. We have two hybrid methods, Delight and DNF, and DNF is still work in progress. We're starting to venture into the image-based models, and we will hear two talks later about the image-based methods. And we also have developed a few summarizers that can take input from either photometry or PhotoZ to convert them into redshift distributions. So other than the PhotoZ methods, Rail also tries to provide infrastructure to create mock photometry and also evaluate the performance of different photosynthesis methods. So first and foremost, we have creators and degraders. So these two kinds of stages are produced to create mock catalogs. And when we don't have real data, we can learn from a simulation and from previous surveys to generate degraded training set to understand the different kinds of systematic and their impact on the photosynthetic product. And we also are building evaluators into RAIL to after you run the photosynthetic method and get different kinds of metrics on how the photosynthetic methods perform. And this will provide great information to how Rubin will choose the default photosynthetic method that it's going to provide to the users. So I will show one example of RAIL. So Golden Spike is an end-to-end example of RAIL originally designed by Alex. That it really just showcased all the kinds of different kinds of stages and then connect them into one pipeline. So this is not normally what the production will do, but this really showcases all kinds of things. So it starts with using a normalizing flow to generate mock photometry, true mock photometry, apply noise and selection to the training set to produce a mock training set, put them into different kinds of photosynthetic algorithms, produce the model, use the model to get the photosynthetic of the test data, and evaluate the performance. So I will jump into, I don't know, for the interest of time, whether we have time for running through the demo, but in this instance of RSP, I've installed RAIL and really want to showcase that this would work. So this is a notebook of Golden Spike. Let's restart the kernel. I'll start running all cells. I suspect that we won't finish the running of the notebook, but I want to show a few places that about how you define notebook. So this import cell really shows how each stages are imported from a namespace. So here, this cell really showcases after creating the normalizing flow engine, the mock data are produced into selected selected and noisified training set sets. So this stage showcases the informing of the estimators. Yeah, I don't think it will finish for me. So you have to just look at the cells. And this here it shows how to define the estimator parameters and then run the evaluators here. I bet it's spending time training the normalizing flow. That's going to take a while, right? So in May 2024, we released RAIL version 1, and I encourage you to look at some of the notebooks in the link here. And if you want to play with RAIL. And what I really want to stress is that RAIL is still a work in progress, even it's called the V 1.0. It's got most of the core API stable, So we call it 1.0 to encourage more development on code base. But we're still working on better user experiences, handling corner cases, and improving its performance. We are prioritizing production pipeline for DESC and Rubin Y PhotoZ production. So using various PhotoZ, getting its PDF and Redshift distribution estimation. We also want to support PhotoZ related research for diverse science cases. So not just the cosmology, but also other extragalactic science. And we also want to include emerging PhotoZ methods so that Rubin doesn't miss out on the great methods being developed in parallel. So if you're interested in open source development and developing RAIL, please reach out to me and Tianqing as co-leads of RAIL team. I'll take a question.
So where are the notebooks? Like where can we find the notebooks?
So it's in my repo now, but I think I'll work with the RSP repo to see if we can share that the example notebook. I think the first thing to work on is to set up a RAIL environment so that people can use on the RSP. But that's still work in progress.
TQ outside of the RSP, they're all on GitHub under Rail, right?
Oh yeah. Everything is open source, so it's all in the LSST DESC RAIL space. So all the methods are shown here, and that the link will lead you to the RAIL repo for the specific method. Okay. All right. Before I close, I just really want to give a shout out to all the RAIL developers, including those who design and develop most of the code. So Alex, Malz, Samson, and Eric and Charles. I just want to give a big shout out to the main developers of RAIL. All right, moving on. So Grant, do you want to share or do you want me to drive?
You can go ahead and drive TQ. Am I good to start?
Yep, go ahead.
All right. All right, thanks everybody. So my name is Grant Merz. I'm a graduate student at the University of Illinois, Urbana-Champaign. And I'll be talking about my image-based PhotoZ estimator DeepDISC. So a bit of a gear shift from maybe previous content that was kind of, mainly catalog-based estimators. So this will be geared towards just directly taking the image and producing an estimated PhotoZ. So just a little bit of a background on image-based PhotoZs. So it's been shown in various studies that morphological information can help improve PhotoZ estimation, especially in the case of missing or not great photometry. And this can be done by adding shape parameters or adding fluxes computed through different apertures to include that morphological information along with the photometry. But with the sort of explosion of AI and computer vision research in the last decade, there's been a lot of focus on using deep learning algorithms to just directly take an image as input and then through backbones or networks like CNNs, capsule networks, state-of-the-art models like vision transformers, produce a estimated PhotoZ just directly from that image input. Next slide, please. So DeepDISC at its core is an instance segmentation model. So it's maybe a bit more complex than just like a traditional CNN. So it's designed to detect, segment, so assign pixels to a given detected object, and then classify sources. And these are actually sort of built off of, if anybody's seen like those videos for sort of like self-driving cars that are able to identify different objects through the camera attached to the car. This is kind of sort of the foundation that drives a lot of this computer vision research. And so the goal here is to basically just apply those sort of state-of-the-art models to astronomical images. And this was done first by collaborators here at Illinois, led by Colin Burke in 2019. And so this type of framework was applied to simulated images. And next slide, please. And the extension of this work that I'm leading is basically adapting the code base to be able to use state-of-the-art models, so things like those vision transformers that I mentioned earlier, and to really push to try to apply this to real data. So in 2023, we published a work that was a comparison study of different state-of-the-art networks that go into this instance segmentation framework, and then applied them to HSC data, so real co-added images from HSC data release 3, and compared how well they did at that task of simultaneously detecting objects, assigning pixels through segmentation, and classifying them in this case as stars or galaxies. And so there's kind of an example of what that looks like after the networks have been trained, how they can sort of be applied to an image. Next slide, please. So the goal and the PhotoZ aspect of this work is to basically adapt these networks to, in addition to the detection and classification, produce an estimated Redshift PDF for each detected object. And so because these networks are very modular in nature, what we do is add a mixture density network on top of, this is the sort of baseline DeepDISC. And so what that basically does is take the sort of features produced from deep inside the network and feed them through a network which then produces means, standard deviations, and relative weights. So basically parametrizing the PDF of an object's redshift as this Gaussian mixture model. Next slide, please. And I just wanted to also take a moment to really highlight the work done as part of a Link Frameworks incubator. So I had the good fortune of leading this project to basically put DeepDISC, to wrap DeepDISC inside of RAIL. And so this is one of those image-based estimators that TQ mentioned earlier. And it's able to run off of the RAIL sort of backend, the RAIL data IO, while also capitalizing on the abilities of DeepDISC to use multiple GPUs and parallelized training and inference. And so we really, I think, got a nice code base that sort of follows best coding practices, through a lot of the help from the frameworks team, and also got this really nice logo here produced by Kostya at Link. Next slide, please. Thanks. So to get into the actual sort of science results from DeepDISC, so after the sort of the code base has been set up, we wanted to validate on DESC simulated images, so these DC2 or DP0 images. And so we basically can take as input in our training just the 6-band raw UGRIZY pixel values from the co-added images, and then additionally can input the galactic reddening at the location of each object to try to reduce degeneracies between dust reddening and redshift. And then as a sort of comparison and a validation, we compare to 2 catalog-based estimators. So these were mentioned earlier, FlexiBoost and BPZ. Next slide, please. And so here's some preliminary results from that sort of comparison and validation. And so these scatter plots are taken from the modes of the estimated PDFs for each method. These are all sort of the same set of objects. BPZ and FCB were ran and estimated on the object catalogs to try to get the sort of prior information as similar as possible to just using the direct images. And in general, we get across the sort of full sample of objects in the gold sample. So this is magnitude limited up to I-band 25.3. We can see that DeepDISC is performing really well in terms of bias, scatter, and outlier fraction. It's performing better than either of the catalog-based estimators across this entire bulk sample. Next slide, please. And another way in which we can test the validity and compare our PhotoZ estimates to the other methods is looking at the quality of the PDFs produced. So one way of doing this visually or qualitatively so this basically characterizes sort of how broad or how narrow your photometric redshift errors are. Ideally, the pit histogram would be flat, a uniform distribution between 0 and 1. And so visually, you can kind of just quickly diagnose that DeepDISC is indeed producing the flattest pit histogram here, and also shown there is the sort of the QQ plot of the pit values, which also should basically ideally be along the diagonal. So again, sort of qualitatively, you can see that is producing really well-calibrated PDFs compared to the other two methods. Next slide, please. Some quick points here. I think in the interest of time, I'll try to sort of breeze through these. But this is just showing sort of the quality of those point estimate metrics as a function of the redshift. Next slide, please. We also looked at the dependence on imaging systematics. So things like the reddening, the blendedness, which characterizes how blended or how close sources are in the images, and also the full width half max PSF across the image. So I had it sort of mentioned in a slide earlier. I didn't explicitly mention, but these are large images, 1.75 arc minutes to a side. So we expect some variation across the field. And then next slide, please. One of the other things we're also looking at was just how the performance improved with image quality. So essentially with more observing time, we would expect the PhotoZ estimates to also improve. And through looking at basically the 1 year's worth of observations versus 5 years worth of observations, we can see that the scatter is basically inversely proportional to the signal to noise of the input images. And so we can kind of use this to get a sense of, after the full observing run, what can we expect our PhotoZ estimates to have? What quality can we expect them to have? And just some concluding points here. Again, I just want to highlight this is an image-based estimator, so it's fundamentally different from catalog-based estimators. It's very flexible. It's able to be applied to images of differing sizes with differing number of objects. So it can be used in a variety of use cases. In general, it's outperforming catalog-based estimators in terms of point estimates and PDF qualities, and appears to be fairly insensitive to different imaging systematics. And that's it.
Thank you, Grant. We'll take questions.
Feel free to put questions on Slack if you don't have any.
So I just want to know, when you feed this galaxy morphology to your PhotoZ algorithm, would that introduce like additional correlation between your PhotoZ and shear measurement that might bias the cosmology in some way?
That's a good question. Yeah, so any analysis of correlations with shear, that's sort of beyond the scope of, currently what we've been looking at in terms of just, taking a large sample of galaxies and just making sure that we're producing, fairly well calibrated PDFs and fairly accurate point estimates. That would definitely be interesting follow-up work. Yeah, I'm not sure if, for instance, yeah, these sort of image-based estimators or estimators that use morphology as input. I don't, to my knowledge, I'm not aware of any studies that have looked at those correlations and how they relate to shear. I think mostly, the sort of traditional methods are those catalog-based methods. So that's an interesting follow-up, but no, we haven't looked at that.
Yeah, just as a comment, so any catalog-based methods are correlated to shear because photometry is correlated to shear. So it's a more general issue than just the image-based stuff. Thanks, Grant, again. So let's move on to sorry.
The recorded.
Yeah, we have another recorded.
Okay. Yeah, there's one more talk that's recorded because time zone difficulties. If you have questions about this one, definitely put them on Slack. We should respond by tomorrow.
I'm a postdoc at the Max Planck Institute for Extraterrestrial Physics in Munich in Germany. It's a pleasure to speak to you today. I'm sorry I can't present live or in person. I'm traveling for the LSST AGN Science Collaboration meeting in Italy this week, and it's a difficult time for me in Europe. So yeah, today I'm going to be talking about photometric redshifts with RAIL-LePhare. RAIL, I think a lot of the audience here is probably familiar with, the redshift assessment and infrastructure layers. And LePhare is a photometric redshift fitting code using template fitting. LePhare, some of you may know, is actually French for the lighthouse. It comes from the acronym Photometric Analysis for Redshift Estimation. Very proud of our new logo here in the middle, which was developed as part of the Link incubator, which I'm going to be talking about. So I'm working on the German in-kind contribution to LSST. This started in April 2023. And really to focus on the AGN side of LePhare. LePhare development has previously concentrated on galaxies. There's a new AGN module that's been developed, and we're really trying to work on the performance of that. eROSITA is a key focus of our work. It's the X-ray telescope built at the Max Planck Institute for Extraterrestrial Physics. It's not taking data anymore, as I'm sure a lot of you know, but that's giving us lots of X-ray samples to do AGN science with, and that's what we're concentrating on. LSST will be a big part of that. There's a big overlap between eROSITA and LSST. So we're developing capacities both for LSST only data, but also just general functionality for LePhare, including for even the very multi-wavelength data sets that come from the fields like Cosmos or the other deep LSST fields. So we're just working on the general development of LePhare. I'm focused on AGN, but I think all of the work we do is relevant for galaxies too. And just a quick key point that we're not performing large-scale production runs as part of the in-kind contribution, but we're trying to develop the code such that it can be run at scale, possibly by other projects. So the key question I think a lot of us have is templates or machine learning. What are the benefits of each? How do we use them together? I think my conclusion is quite clearly going to be templates and machine learning. We want to use both, and we want to use them both for different things, and we want to use them together if possible. So machine learning has very high performance on samples inside the training space. It's fast to run after training, possibly has poor handling of rare objects. If the objects aren't captured in the training space, we don't expect it to perform well. And of course, it requires retraining on new data. When we have new noise features or deeper data or anything like that, we need to retrain because it will affect the results. Template fitting is physically motivated. It's a real advantage. We have these physical SEDs, which we're fitting. No training set required. Slight caveat, we can use training sets to fit 0-point offsets, but effectively can be run without any training. That means we don't have a training set bias, and we can probe new regimes It's statistically robust. It's based on very well understood chi-squared minimization statistics. There's a huge literature on that, and I think that means that we understand the meaning of things like errors. We understand how the errors are generated and what they mean. The only method available for small samples is another key feature, of course. If we have very rare objects, I think the most striking example of that would be the really high redshift objects in the JWST deep fields, where you can only really do that sort of work with fitting. Just want to quickly look at some color redshift relations. This is for AGN, but the points I'm going to make are very general. And this is from the EFEDS USITA Final Equatorial Depth Survey from Marz's paper from 2022, Marz Alberto. The top line is IZ and W1, W2 color redshift relations for point sources, and the bottom line is extended sources. That's a key part of how we break our samples up to perform to calculate redshift for AGN. And it just I think this really clearly demonstrates the difference between the two methods. So the black points are spectroscopic objects, and the coloured lines are templates. So we take a given template and look at its colour as a function of redshift. And obviously for machine learning, we're measuring some colour, say 0 here, and then we're looking across the redshift space and we're saying where is the highest density of training objects, and we're effectively kind of fitting a distribution in that colour space. That's quite a different thing to what template fitting is doing, where we're for a given colour, we're looking at the templates which fit that, and we're excluding certain templates and then marginalising over the templates to get the redshift. And I think this shows you, for a given set of templates, we have regions here which are completely not covered by the training space. Now that might be a good thing, that might improve our results. Perhaps these templates don't exist at this redshift, but I think it shows you the sort of key difference between the two methods. And obviously that, as it gets generalized to higher dimensions, is the same basic procedure, and I think that's sort of a key thing to understand about the difference between the two. So LePhare, as I mentioned, the photometric analysis for redshift estimation code, originally a Fortran code developed over 10 years ago, performed spectral energy distribution fitting using templates from spectroscopic measurements. There's a new C++ version here. This is the official version that we want people to use if they're doing science. I'm going to be presenting a newer version on GitHub, but that's not the official version, so please use this version for any science you're working on. There's a Python interface, which again is under active development, and stars, galaxies, AGN are fit separately. It's another advantage, arguably. We have a best fit chi-squared for each of these, and we can then use it for even classification, and we have available best AGN model fits for every object, so we can produce samples after the fact if we've run LePhare on every object. And again, as I said, it's a chi-squared fitting template selecting model code, essentially. So the LINC incubator. LINC is the LSST interdisciplinary network for collaboration and computing. This is a $22,000 grant for us to collaborate with software developers, particularly Drew Oldag and Olivia Lin. Also Jeremy Kubica, Johann Cohen-Tanugi was contributing on our side. He's also heavily working on LePhare for DESC in particular. This ran from February to May 2024, involved a C++, Python rebase. In actual fact, most of the C++ code and algorithms remained identical. Most of the work was on the continuous integration, continuous development, using all of the GitHub actions to really improve the testing, publishing to PyPy, all those sorts of things that contribute to good code development, but the actual algorithms weren't drastically changed. And building the RAIL interface via Python was a key outcome of the incubator, and that's something that is I'm also working on as part of the in-kind contribution, but it's important to make the political point that the work that was done in the incubator does not contribute to the in-kind contribution, and I think the incubator was really focused on the CI, CD, the GitHub transition, starting the RAIL interface, although I think I took over the lead of that quite quickly. And things like pip install LePhare was absolutely a contribution of the incubator, and quite distinct from the in-kind work I'm doing. But yeah, pip install LePhare I think is another major achievement. Please experiment with that. As I said, this is not the official version, but the algorithms haven't changed, so we're testing the robustness now, but I'd be really keen for people to test and experiment with that. And hopefully we've made it much easier to install and run, and we also worked on the documentation, which has hopefully improved. Okay, one of the key advantages of RAIL is the visualizations we get. These are the probability integral transform plots that we're all using to check the quality of the posteriors. We see here the standard LePhare run is under dispersed. I've been told the way to understand that, if it looks like a U, it's under dispersed. That means that the posteriors are overly tight, effectively. And we're working on broadening those posteriors either by Gaussian smoothing or adding in systematic errors, as we know that these templates are not fully capturing the redshift color space. I think that's why we're overconfident, and that's using these pit plots. That's something we can calibrate and improve our error performance. Key thing I'm working on is a clouds data set. It's a Canada, France, Hawaii telescope large area U-band survey, which is adding in the U-band to Hypersphere Prime Cam, and I think therefore giving us some LSST-like data. And a great thing about RAIL is then we can instantly compare to the other codes that are available in RAIL, so particularly KNN and FZ Boost. And as we expect, we are seeing increased performance. I don't expect you to read the actual performance there, but we're getting about 1.4% for LePhare, 1.6% for LePhare, 1.4% for KNN, 1.2% for FZ Boost. So we are seeing increased performance with the machine learning codes. And this is for an I-band limited sample of I below 22.5. And I'm including BPZ there, but don't look at that because I haven't updated the filters yet. So these results are uncharacteristically poor, I think, for BPZ, but we're also going to be comparing for BPZ. All I need to do is update the filters to the CFHT and Hypersphere Prime Cam. Key thing that I'm using RAIL for at the moment is looking at degraded training sets. So this in blue is the total I-band distribution in the clouds sample, and then the orange is the spectroscopic sample. Obviously peaking at a much lower magnitude, we've got a brighter sample, and I want to see how that affects the results over the full sample. I'm going to do that by degrading the training sample further and just see the impact. So very simple test I did, just looking at limiting the training sample. So doing the train test split, leaving the test sample as it was, going up to all magnitudes, but limiting the training sample and showing how that, we know what that's going to do as we really limit the eye training sample to very bright 20th magnitude. We've suddenly failed to capture all of the high redshift objects. And then as we move up to higher magnitude, including more of the sample, we recover the full performance. As I said, this is something we understand. We know this is a feature of machine learning, but it's important to I think, measure it and see the impact it has, and therefore force ourselves to only do science with samples which are selected to represent the training spectroscopic sample. Classification is something that comes out for free, I think, with the template fitting. So as I said, we fit a best star, best quasar, or best AGN, and a best galaxy, and then we have a chi-squared for all of those models, so we can use those chi-squareds to classify. Just quickly looking here, this is the receiver operator characteristic curve. So false positive rate on the x-axis, true positive on the y-axis. So our ideal classifier will be up here. We get 100% true positives and no false positives. And again, we are outperformed by machine learning standard neural network classifiers, but we've given all the drawbacks. I think this is still useful. We still have some performance of the chi-squared ratio between AGN and the galaxies to selects AGN, and this is selecting the Marchesi Chandra X-ray sample. So just using the UGR-IZY photometry, selecting Marchesi X-ray detected objects. I think that's a useful feature of template fitting. And machine learning codes, but we're starting to compare it all, and that's one of the real advantages, I think, of using RAIL, is it's going to allow all these comparisons. Future work, things we could work on, things I am working on. So I think optimizing the hyperparameters for performance and speed on LSST. Do we have a max runtime per object? We're going to have to set the Redshift grid, number of templates, all those things if we do have that, and we need to optimize for that. How much CPU time per object do we have to play with? If that really becomes a problem, is an emulator something we're thinking about? I know in Euclid, that's one of the things they're doing is running template fitting over a representative sample and then using something like nearest neighbor again to then make an emulator for the template fitting codes. In theory, you then have the advantages of the full coverage of magnitude and redshift space, but with all without the degradation that you get from the machine learning codes, and you still get the speed from using an emulator possibly. Also a generator, so we can take the Cosmos samples, for instance, use the full multi-wavelength catalogs to generate the best fit templates, and then use those templates to generate LSST photometry that can be useful for testing the machine learning codes and possibly other purposes. So to conclude, I'm working on a 3-year in-kind contribution developing spectral energy distribution fitting for AGN in particular, for LePhare. I'm now concentrating on the prior, including looking at redshift priors from other sources, possibly from variability, possibly using machine learning, redshift posteriors as an input prior to LePhare, and then just using LePhare to look at the templates, or look at, for instance, stellar mass from the Raphael and Shirley templates is one thing you could do using redshift priors from a machine learning code, for instance. I want to present the work that was done in the Link Frameworks Incubator. Key part of that is the pip install LePhare. I think that's really helpful to us, making it easier to install on Macs and other systems, and that's been great. Very grateful to Drew Oldag, Olivia Lin, Jeremy Kubica, Alex Maltz, and others. That's been great for us, very helpful. But as I said, I want to make it very clear which work is done as part of the incubator and which work is done as part of my in-kind contribution, which is focusing on AGN. So LePhare has been incorporated into RAIL. That was started in the incubator. I'm still going to, of course, keep working on that. Please get back to us with any issues if you've been testing that or found any problems. Please let us know. And yeah, optimizing templates and parameters for LSST for both UGRIZZY only and for the deep filter where you have better coverage. For galaxies and AGN, that's the focus of our work going forward. How do we optimize the hyperparameters essentially? And that's a similar problem, I think, for machine learning. We could probably use some of the same infrastructure, how we do this hyperparameter optimization. So yeah, thanks very much again. Thanks for listening. I hope I haven't overrun too much. It's 15 minutes. Sorry for taking up your time, if so. And yeah, please get back to me with any questions if you wish. Thank you. Bye-bye.
If you have questions for Raphael, please send that through Slack and we'll communicate with the speaker. Okay. Yeah, I can drive the slides. Okay. Or, yeah. Sure.
Hi, hey, I'm Noah Weaver. I'm a postdoc at Berkeley, just across the bay. And so I'm here to chat a little bit about some of the work that we're doing on trying to figure out some of the synergies between DESI or other spectroscopic surveys and how we can actually leverage sort of cross collaboration to actually improve some of all the hard work we're doing on the PhotoZ side. So. So I'll skip over a lot of the intro in the interest of time, but PhotoZs are important for cosmology. And they're also a really big part of our error budget right now. So LSST, Rubin, is going to have a lot of data, but current surveys are actually systematics limited in a lot of ways. So that doesn't bode super well unless we can deal with these systematics. Okay, so obviously, as you all know, really it boils down to learning a redshift from this broadband photometry, and there's lots of different recipes for doing that. You've heard some of them today. The thing is, we don't actually necessarily need per object redshifts in actuality for at least the types of cosmology that we do in these sort of key projects right now. This 3x2 point cosmology, we really just need the distribution of each redshift bin. But of course, being able to get object level redshifts helps us to bin much better and optimize that binning. So there's lots of different ways to do this. A key challenge, as you just heard in the last talk, is that spectroscopic samples that we have right now are not represented. So when your training set is biased, you basically are probably going to have some biased predictions, and it's actually very hard to know how biased you are if you can't actually quantify how representative or non-representative your spectroscopic data sets are. And the spectroscopic data sets that we have inherit a whole mess of selection functions because they're all targeted off of different imaging surveys, which themselves have sort of implicit selections based on their imaging properties, which are then in their object identification, which are then targeted based on other spectroscopic surveys, which then themselves so those are explicit selections but then there's some additional implicit selections based on which one of those actually gets successful redshifts. And so then you aggregate all of these, and now there's your training set, and now quantify how biased it is compared to some sample from Rubin, which we don't have any, which we really have no way of quantifying how far off that is. So that poses a really big challenge, and is of course totally invisible to types of things like holdout tests, where you're testing, you're still assuming the training set is representative. So you can do things like the last talk just talked about, where you try to sort of, prune your training set down and estimate, okay, how biased would I be if it's not representative? And the answer tends to be it's like pretty biased. But of course, in that case, you still know how biased the training set is, which we don't. So it's an unknown unknown. Whew, okay, so it's hard. So there's a lot of methodological freedom to try to account for this. The problem is it's really hard to quantify the statistical uncertainty that comes from turning all of these methodological knobs. So here's an example case with the dark energy survey, where I work also. So Giulia Giannini did this, looking at applying some of these different photo Z codes, all of which were listed in one of the previous talks as being one of the sort of primary things being looked at or incorporated. So we have this SOM-PZs, DNF, and then WZs as clustering redshifts. And so you're incorporating the clustering redshifts to try to calibrate out some of the residual uncertainties from these other methods. And it turns out that it actually really depends on the choices you make for these. They can actually have pretty significant impacts on your inference. So you can have pretty big shifts on your S8. And so that's something that we want to actually incorporate into this theoretical uncertainty. But again, it's pretty hard to quantify that. So luckily, we have really nice improvements in technology on the spectroscopic side, because no longer are we drilling plug plates and manually plugging in fibers, but we actually have new telescopes where we can actually gather 5,000 redshifts at a time and tweak them, and within a minute be gathering 5,000 more redshifts, and so on and so forth, to get 10 million redshifts per year for DESI, which will increase with future spectroscopic surveys. And we can also go from identifying potential targets to within a couple hours actually redshifting them. So that also means that we can actually have target of opportunities with a turnaround on redshifts very, very quickly. So this is great. And so what does that mean in terms of how we could actually help augment some of the current really challenging aspects of photo Z estimation, such as these unknown unknowns? So one of the ways is, well, let's just actually directly target off of a sample and just see what the redshifts are, see what the objects are, and map it out. Let's just target a fair subsample that cuts out all of these complicated systematics that we're spending all this time trying to handle. That is one thing that we propose might be worthwhile. One of the challenges means we actually have to work across collaborations. That can be easier said than done, but I think it would pay off and be worth the effort. One thing I'm particularly interested in is actually not just, say, estimating the redshift distributions of the samples that you have, but actually thinking of those as sort of proto-samples, proposed samples, which you're then able to sample some subset of, get a few pointings over a couple nights, and now you can actually have a nice fair sample over your color magnitude space. You can identify where do we have all the redshift failures. Let's cut those guys out. And now we have nice spectroscopic support where we actually trust our photo Zs, and we actually even know what the objects are. So that is what we're proposing. Maybe I shouldn't have called it direct calibration, because there's another thing called direct calibration, which is like taking your existing spectroscopic redshifts and reweighting them to make the magnitudes look similar. So my bad. Maybe we'll change that. If you have suggestions, you can talk to me. So we did a test case of this just with the DeepDISC lenses. So we just took a single pointing, 12 minutes in bright time, and we looked at the lowest 3 redshift bins where the redshifts should be, the photo Zs should be pretty much the best. It's the brightest, and also it was, given the limited amount of time that we were given, what we could observe. So we got a single pointing, it's about 8 square degree field, and this is the filled in is the sort of is the magnitude distribution of the whole, all the DES lenses, and then the outline is the spectroscopic targets that we got. So this, we got about 3,000 total with this number in each of these bins. Very high success rate by design. And one thing. So let's look at the redshift, the photoz's versus the spectroscopic redshifts of the objects themselves. So there's not looking at all of the lenses. I'm just looking at the ones that we targeted. So it's apples to apples, and one thing pops out, very clear. So that's kind of interesting. And so that's useful. That tells us, let's dig in, let's figure out what's happening here, okay? So clearly this is, well, not necessarily clearly, there's sample variance, et cetera, but it seems to be not due to sample variance. This is statistically fairly significant. And so if we actually look at the nuisance parameterization that we use in DES, so we include some shift and some stretch parameters to absorb residual uncertainties in the redshift distributions. And we look at the posterior sort of mean for those parameters from the actual DES analysis using all of the lenses and all of the sources. And we actually apply that to this blue sample, which is the photoz's. It turns into the black sample and perfectly absorbs essentially the mean and the stretch that we would get if the spectroscopic redshifts were correct. So that suggests that this is actually happening throughout the population. The SOM-PZ estimate also doesn't really capture this. If we look at one of the things that might cause this type of effect, not claiming this is exactly what's going on, but just to illustrate the types of training bias that might show up as something like this, is you have this redshift color to degeneracy with DES, we have GRIZ, and we have these two different types of galaxies, which looks pretty similar at 0.3 and 0.5. And so one can imagine that if you had your training set had more of the 0.5 to 0.3 relative to the DES lenses, then you might be misclassifying a bunch of these 0.3 galaxies as 0.5 and maybe get something like this. So that's one example of how a training set bias might show up, but might be hard to detect. The error bars here come from looking at simulated DESI pointings of buzzard simulations and show the statistical significance of this bump. And I'm going to maybe skip over this, but basically going from a single pointing to the full population, you can do some reweighting to account for sample variance, and this works better than in, say, the typical SOM-PZ approaches, where you're not necessarily sure, you're not totally confident that you have all of the dimensions necessary to account for the different selection effects, because we selected it directly on the targets themselves. We basically know that this is a fair sample modulo sample variance. So if we just do some basic fitting, just fit a Gaussian mixture model and run this through a cosmology pipeline, we can get a sense for what types of effects we might see, what are the size, and we can see something like this 2x2 point analysis from orange to green. We get about a 1 sigma shift in S8. Now, again, this is 2x2 point, not 3x2 point, and this does depend on how we actually smooth the redshift distribution, right? So if I did a KDE with different bandwidths, for instance, that S8 contour will shift around. So take this with a grain of salt. This is a single pointing. We need more data to really say much more on this. Conveniently, we did just get new data last week, so managed to get 3 partial tiles through to get more data that we'll be able to analyze and see if this persists and what the implications might be. So this is just a test case to demonstrate the types of unknown unknowns that might show up, that it can be really useful with 12 minutes of spectroscopic observation that can pop out and account for, say, many of our hours of work to identify and mitigate otherwise. So there's a lot more into this. In the interest of time, I'm gonna have to breeze through, but basically one of the things I'm particularly interested in is, okay, here in the photo-Z error space, if I look at this color magnitude space represented, say, in a SOM, then I can see, okay, I have actually my error is scattered around. There's a few points here where the photo-Z's are actually quite bad relative to spec-Z's, but I can also see there's in that same region, I have a lot of redshift failures. So I don't actually trust my spectroscopy there. And so I can actually identify that and potentially, and then motivate, maybe I'll just cut that out of my sample. And so I can throw out my 0.5% of my objects and throw out the vast majority of my spectroscopically biased corrections, and leave myself with just color magnitude space where I have good spectroscopic calibration, but maybe my photo-Z's are not great. If I look at a higher number density, then I can see this a little bit more clearly. So this is looking at 50,000 spectra. Another thing I can look at is how does this sample, I can identify contamination. So, oh, look here, there's a bunch of stars left over in my sample and a bunch of quasars, even though I've applied cuts to remove those. So that allows me to prune those out. So I now can remove something like 2% of my photometric sample that is dominating sort of the systematic contributing to my systematics budget. So this type of sample pruning is something I'm excited about. And to actually do this on Rubin, we would need to actually get much more data at much higher redshift. We have 7,000 objects from this Pathfinder program that Victor DeepDISC, Jeff Newman, myself, and others put forward, but we need more. Basically, what this would look like is, so what I'm showing here is essentially how long it takes us to get good redshifts for half of the galaxies in a given bin. So at the very faintest end, going out to 24.5, this is very minimal cuts. This is from HSC. It takes us about 2 hours to redshift half of those galaxies, but it takes us 10 times that to get the next 40% of galaxies. So what we want to do is basically identify where do these live in color space, so we can throw out the few galaxies that dominate, that are really, really hard to get good spec. Our photoses are probably never going to be able to determine, and let's limit ourselves to where we actually have good spectroscopic support. We don't have enough data to really be able to do that very well. You can see how noisy it is, but we would love to motivate with quantitative sort of analyses of how bad are the photoses likely to be with Rubin, given this. If we can't redshift them with DESI, do we think we really can redshift them with other things? I don't know, that's going to be hard. So we have to somehow quantify these unknown unknowns so we can justify actually putting in these, few night observing times to build up this data set. So that's something I'd like to do. If you're interested, feel free to come talk to me. It'll require working across these collaborations, but I think it could be really fruitful if we start getting that ball rolling and reducing those barriers to actually, gaining from the synergies between these two types of surveys that otherwise would just have to operate independently. So sorry for going. Ooh.
It's not time for questions, but put them on Slack and we'll keep going with one more. Sorry. No, are you ready?
Everybody, should I start?
Yes, go ahead.
Yeah, hi everybody. I'm sorry I'm not there in person. I'm here in Palo Alto, but I got something on the plane and I have a very bad cough, so I'm not going to spread it out. I'm going to speak about the other network that's been installed in RAIL for estimating photometric redshift on galaxy images. The work was mainly performed by Valentin Breck and Théophile Noble, who were two engineering interns at our university, the University of Paris-Cité, and I am at DPC and 2P3. With the contribution of the people listed here, so Michel, Eric, Francois, Alex, and Marcus. Next slide. This is part of a DESC project, 318. You see there are many more people participating to that, where we want to test and validate several machine learning techniques to estimate photometric redshift using multi-wavelet galaxy images. And we have a Slack channel where you can join and discuss with us about these techniques. Next slide. So the network that we have installed in RAIL is the Inception Deep Convolutional Network by Pasquet et al. 2019, that as I already mentioned before. So this network has been demonstrated to be highly performant on SDSS images, and we took it at first like it is. So we just made the interfaces in RAIL, because after testing with respect to many other networks, is still the most performant on SDSS images with respect to all our tests. Next slide. So we use as data metrics a sample of 30,000 images from SDSS with the training sample 15,000 for validation. As metrics, we use the usual metrics, the residual, the median absolute deviation, and the fraction of outliers. Next slide. We checked several CNN, ResNet, and Transformer networks, and the best was always the Pasquet et al. 2019. And you can find our analysis in the PCW 2023, where I've shown more of these tests. These are the results that we have with a very low bias, very low fraction of outliers, and a very good sigma MAD, applying these two images from Day et al. 2022. I guess this is a previous version of the last one. Okay, very good. Next slide. So we installed the Inception network in RAIL, and you can use it just calling RAIL Inception. And this is the complete Pascal 2019 network like it is. And then we spoke last year about the possibility to improve the learning process with regularization and dropouts. And this is what we have done in 2024. Next slide. And so the architecture of the Inception module using Pascal is pretty complicated with several layers of convolutional, average pooling, etc. So what we did with the Théophile is to take out some of the modules to see if the network could be more efficient with less layers so that it can go faster and be much simpler to use. So next slide. Théophile tried around 40 inception network variations, and he found some simplified versions that are more performant than the original. And we improved also the network with regularization and dropouts. Unfortunately, we couldn't increase the image training sample at low AIZ as we would have done to reduce overfitting, and we could not yet test and validate on TC2 simulation images. And we could not apply it to HSC images and compare to other PhotoZ catalog. We also wanted to include possible bias, extinction depth, etc. But unfortunately, the intern that came after Théophile didn't advance much, but we will do it in the future. Next slide. So what I really want to discuss at this meeting, since we are all here, is how to integrate this effort in commissioning PhotoZ catalog production, which computing resources we can use. So right now, we were using NERSC and the CC and 2P3, but we were wondering if that will be enough for the future. We also found the biggest difficulty of this year in 2024, not to have image simulations and biases on which we could test the network. We asked for help in the Slack channel, but we didn't have much help. This intern that we hired that unfortunately didn't work on this at the end was supposed to create an archive of galaxy images on which to test the network from DC2. And I'm wondering, since we have a flow for mock catalogs, so that you saw that in RAIL there is a flow to create mock catalogs, to degrade them, and then test the networks. I was asking myself if we could have an analog for galaxy images, like the other network, DeepDISC, has been applied to these images, and I'm wondering if the archive can be shared so that we can apply both networks on the same archive of galaxy images to see the results. What worries me the most is the size of this archive, because I've seen in the previous talk we have thousands of images on which the DeepDISC was tested, if I didn't make a mistake, because I have fever. But actually the Inception network was tested on hundreds of thousands, and now we can have millions of galaxy images. So I was wondering how we go from this step to the next step, where we can test our networks on millions or at least 100,000 images, galaxy images, and how to create this archive. So I wish I was there to discuss it in person, but I think that is an important discussion. Next slide. I think is last one. Okay, perfect. Thank you.
So that's all the talks. So let's give a round of applause for all the speakers again. Hopefully, so we don't have more question time, but hopefully these talks kick off more discussion during the rest of the week. So yeah, we'll see you in later sessions. Thank you for attending. Thanks everyone for attending online. Well,
Thank you.
Thank you.
I tried. Yeah. Yes.